And that is, years ago, we measured the magnetic field of Mercury with a robotic, I think it was Viking. I think that was the name of the robotic ship that went out there and measured Mercury's magnetic field. Well, NASA is now sending another robotic ship called Messenger out there. Messenger's supposed to be there in 2005. Well, over the time between Viking and Messenger, Mercury has had enough time for its magnetic field to decay measurably. So he's saying when Messenger flies by Mercury, Mercury's magnetic field ought to be about 4.2% lower than Viking measured it to be. So if that turns out to be true, that's another validation of his theory. Interestingly enough, there's another prediction on here that I don't have that he made that's interesting too. Both his theory and the dynamo theory predict that planetary magnetic fields under certain conditions can reverse. His theory predicts those reversals to be very rapid, on the order of months. The dynamo theory predicts these reversals to be very, very slow, on the order of hundreds of thousands of years. Well, in 1995, a team who was looking at very thin lava flows noticed several very thin lava flows in which the magnetic components of those lava flows kept twisting back and forth just over the course of a very thin layer. And the argument is that the lava is laid down. As it's still liquid, the magnetic materials orient according to the magnetic field. And then when it freezes or when it solidifies, those things can't move anymore. Well, if those lava flows are very, very thin, you would expect then those reversals to have occurred very, very quickly. That can't be accommodated in the dynamo theory, but it can be in the rapid decay theory. Now, what's interesting about this is here you have, this is exactly what science is all about. You make a few observations. Then you use those observations to develop a hypothesis of what's going on. Then you use that hypothesis to make predictions about what other data should look like. Then you go out and measure that other data. This is what this guy has done, and he comes up with a very effective magnetic field theory. Now what's interesting about this magnetic field theory is if it's correct, if his idea of how these planets are formed, how the magnetic field sets up and so forth, and how it decays is correct, he has a maximum age limit for the Earth of 9,000 years. Now, is this a correct view? I don't know. I can tell you right now, based solely on science, this is a much superior scientific theory than the dynamo theory, because it's consistent with the data and it is predicted data that wasn't known at the time. That makes it a seriously better scientific theory. It doesn't get much press, though, because it predicts a very, very old or a very, very young Earth. And that's not palatable to a lot of people. Okay, there's another way we can date the Earth, too, using radioactive decay. In radioactive decay, we have a radioactive atom that's unstable for one of many reasons. In order to become stable, the nucleus actually breaks apart or ejects some particles. And as a result, you make a completely different atom plus a new particle. And if you're worried about the dangers of radioactivity, it's all right here. It's that little particle that the nucleus is shooting out. That particle has a lot of energy, and if it happens to interact with your cells, it can kill them. Or worse, it can mutate some of your DNA. So in the end, that's the danger with radioactivity. The chemical itself, not a problem. It's that little particle it's shooting out that's the problem. Okay. Now, radioactive decay is interesting because there are a lot of radioactive isotopes, and they all seem to have different rates at which they decay. Typically, we express this in terms of half-life. Half-life means if I have 100 grams of a substance, and it decays by radioactivity, over the period of its half-life, it will decay to half that amount, or 50 grams. And then over the next half-life, it will go from 50 grams to 25 grams. That's what half-life means. Some radioisotopes have very short half-lives, on the order of nanoseconds. Other radioactive isotopes have very, very long half-lives, on the order of hundreds of millions of years. And so these half-lives, we assume they occur they're pretty constant. We should be able to figure out how to use this to date. For example, only radioisotopes with short half-lives that exist here are those that have a process of being renewed. For example, carbon-14. Carbon-14 has a half-life of 5,730 years. If it were not consistently renewed by some process, after about 100,000 years, it would completely decay away. All right? But there's carbon-14 around. The reason there's carbon-14 around is there's a process in the upper atmosphere that's producing it. Because this process is producing carbon-14, it's continually being renewed. Without that process, there wouldn't be carbon-14 around. Well, it turns out if you look around at the radioactive isotopes that we assume should be fairly common, there are at least 11 radioactive isotopes, like lead-205, that have half-lives between 1 million years and 80 million years. But they can't be found anywhere in the solar system. Now, if the Earth were fairly young, you would expect to find these radioactive isotopes. Because if the Earth were, let's say, 9,000 years old, like the rapid decay theory says, something that has a half-life of 1 million years wouldn't have time to decay away. All right? And in fact, you go out to something that has a half-life of 80 million years, it should take something on the order of 1.6 billion years for that stuff to go completely away. The fact that we don't see any of these short-lived radioisotopes is actually evidence that the Earth is at least hundreds of millions of years old, probably billions of years old. And this is probably one of the main pieces of evidence that folks who believe in an ancient Earth use to indicate that the Earth is old. Because if it were young, at first glance, you would expect radioactive isotopes like this to exist, because they shouldn't have had time to decay away yet. However, if the Earth is really hundreds of millions, if not billions of years old, then all of these guys have had plenty of time to decay away. And since there's no process to remake them, you would expect them to be gone. And this is probably what I consider the most compelling evidence that the Earth is old. However, this does make a big assumption. And the big assumption has been challenged in recent years. And I have to tell you, I've been drugged kicking and screaming to this conclusion because I didn't like it. But it seems that the assumption that radioactive decay rates are constant is in fact probably not the case. We don't know this for sure, but there are several lines of evidence that have come out, especially recently, indicating that radioactive decay rates haven't stayed constant. And like I said, I've been drugged kicking and screaming to this because I don't like this. As a nuclear chemist, I would like radioactive decay rates to stay constant. That makes my world a lot more ordered and a lot prettier. However, it doesn't seem like that's the case. For example, a fellow by the name of Riefenschweiler, and the reference to the Physics Letters A article that he wrote is in the notes, showed that the decay rate of tritium, which is a radioactive isotope of hydrogen, varies by as much as 40% when you change the temperature in the presence of titanium. Now, he has no explanation for that. Actually, he is so desperate for an explanation, he reaches for cold fusion as a possible answer to this, and most people have pretty much rejected that idea. But nevertheless, he's so desperate for an explanation, he reaches as far as cold fusion to try to get one. No one really understands this. We don't have any theoretical models as to why. But it seems that just the temperature and the chemistry is affecting the radioactive decay rate. As a nuclear chemist, I would not expect that. Because the idea is chemistry occurs on the outside of the atom. The atom is the shell of electrons with a concentrated nucleus in the center. That shell of electrons should be shielding this nucleus. And when I do chemistry, those nuclei don't enter into the chemistry at all. It's only the electrons. The atoms exchange and share electrons, and that's what runs chemistry. Now, if it was just chemistry, things like temperature and titanium and so forth, that shouldn't affect the nucleus, because the nucleus is way deep inside that electron shell. But somehow it's happening. That's a little bothersome. Bosch and others show that if you actually take all of the electrons away from an atom, so you do what's called fully ionized state, you pull all of its electrons away so you've got a naked nucleus there, the radioactive decay rates in beta decay can vary by as much as a factor of 1 billion. So they can become 1 billion times faster than what they were when the electrons were there. Now, this isn't as surprising, because once you've removed those electrons, the nucleus is fully exposed. Lots of interesting things can happen. What's interesting about this is this fully ionized state occurs quite frequently in plasma physics. And a lot of folks invoke plasma physics to discuss the early stages of the universe's formation. So although we don't see fully ionized states today, except on the very light nuclei, it's possible it could have happened as a part of the universe's formation. Probably the most compelling evidence that really finally drugged me all the way is an analysis